So our final speaker tonight is Arav Saherwala, a Master of Science student in the Department of Chemical Engineering, working under the supervision of Professor Nathalie Tufenkji. And Arav's going to talk to us tonight about a novel detection method for nano and microplastics in aqueous environments. Please go ahead, Arav.
It's Friday night, and you've been craving seafood all week. So you head over to your favorite restaurant and sit in front of this delicious meal. And what you think you're eating is a bite of this fish, but what you're actually also eating is this. To be a little bit more precise, it's these tiny micro and nanoplastics that could be inside your food. Now it's probably hard to see them because they're very small. That's why I've circled them for you. Since the 1960s, we've thrown out 4.89 billion tons of plastic into the environment and landfills. Once they end up there, they go through weathering conditions, such as the exposure to the sun, changes in temperature, as well as mechanical degradation. So that water bottle that you just threw out 10 years ago breaks down into smaller micro and nanoplastics. Now, these nanoplastics are extremely small. Let's talk about how small. Your hair, the tip of it, is about 70 microns, which is something we can see with our eyes. Red blood cells that flow throughout our body are about 8 microns, something that we can't see with our eyes. These nanoplastics that we're generating can be smaller than 1 micron in size. This is much smaller than the red blood cells and orders of magnitude smaller than the hair. So you can imagine why it would be so difficult to detect these nanoplastics in aquatic environments. Because of their small size, the fish at the very bottom of the food chain, the smallest of the smallest, can feed on these nanoplastics. Then the fish higher up on the food chain, such as salmon, will eat these smaller fish, and these nanoplastics will start bioaccumulating up throughout the food chain. Then, of course, when we have seafood as part of our diet, these nanoplastics can enter our body. Now, because of their small size, these nanoplastics can also translocate. What this means is that they can move to different parts of your body, such as your kidney, your liver, or even your brain. So, to recap, nanoplastics are extremely dangerous because of their small size, making it difficult to detect in the environment. They bioaccumulate through the food chain, and they can translocate to other parts of the body, such as the brain. Because of these potential dangers, researchers are focused on detecting nanoplastics in the environment, because if we can measure them, we can do something about them. This is very similar to what happened when we found out there's heavy metals polluting our environments. We figured out protocols and strategies to limit their impact to the environment as well as human health. We need to do the same thing with nanoplastics. So let's go over some of the techniques that are being used to detect these nanoplastics. We're going to look at them based on 2 metrics. Time, how quickly or slowly can a certain process detect nanoplastics, as well as quality. Now, what I mean by quality is 3 things. Number 1, is it sensitive to nanoplastics? Because remember, we said that they're really small and hard to detect. Is the process that we're going to be using reliable? Is the procedure going to be reproducible? And lastly, is the process non-destructive? Because we want to make sure that whatever technique that we're using does not destroy the sample so that we can give our findings to the next researcher and they can ensure that they can find out what the impacts of these nanoplastics are. So the first method that we're going to be looking at is visual inspection. Now, visual inspection basically relies on an observer looking at a sample and identifying where the plastics are. Well, this means that different people are going to identify different parts as plastics. So this method is unreliable as well as slow. What about something that's slightly faster? Pyrolysis GCMS. This instrument burns the sample to analyze the gases to see what's inside. Although a very effective method, this instrument burns the sample, which means it's destroying it. So you can't pass on the sample to a toxicologist to find the impacts. If we keep moving down the scale to something like the use of dyes, which are sometimes used to selectively paint the plastics in a sample, so when you look at it through a microscope, you can easily see the plastics. But sometimes these dyes can leach out, contaminating the sample and also misidentifying parts as plastics. If we continue moving down the quality scale, we have Raman spectroscopy, which is an amazing tool as it can differentiate between types of plastics, and it can detect nanoplastics. However, this process is slightly slow, which means it's going to cost a lot of money. One instrument that's in the upper quadrant is FTIR spectroscopy, which, a lot like Raman, can detect and differentiate between types of plastics, but it's not sensitive to nanoplastics. It can only go down to 20 microns. So we need something in the upper right-hand quadrant of this graph. This is where my research comes into play. I'm using enhanced darkfield hyperspectral microscopy, which is just a mouthful to say it's a high-tech microscope. What's high-tech about this microscope is that we get two types of information. We get spatial information as well as spectral information. What this means is that for every single pixel that's on this image, we get a spectrum. Now what we think is that this spectrum is much like a fingerprint, as in it's unique to every element. So if we can use that spectrum to identify different types of materials. So we need to confirm that the instrument actually does this. So we went and did some preliminary testing. We took plastic and we took hundreds of pixels and looked at their spectrums. Here, we're just showing you 3. And what we found is that the shape of this spectrum all falls within this tolerance band. So ideally, if we got another spectrum that looks like this and falls within this tolerance band, then it would be of plastic. But this doesn't tell us if it's a fingerprint just yet. We need to compare plastic versus other elements. So we looked at plastic versus other pollutants. For example, silver. Silver is a common pollutant that can be found as it's used as an antimicrobial agent. If you look at the two graphs, you're probably going to say, well, those two spectrums look the same. Well, the peak for the plastic lies at 600 nanometers. That's the highest point. If the two spectrums were the same, the peak for the silver would also lie at 600 nanometers. However, the peak has redshifted and it's more closer to 700 nanometers. This means that when we look at that tolerance band, silver violates that tolerance. It doesn't fall within the tolerance limit. So this shows that the two spectrums are different and they're unique for every element. We also compared gold, another common engineered nanoparticle that could be a pollutant in the environment. And again, we looked at the two graphs. We can see that there's one peak for plastic and there's 2 peaks for gold. This means that when we look at the tolerance band, gold violates it. We did the same thing with paint flakes, which is another pollutant, as it can chip off shipping vessels and enter aquatic environments. Plastic has 1 peak, and again, you can see that the paint chip has multiple peaks. So you can probably guess that it does not fall in that tolerance band. So far, we have looked at plastic versus other pollutants. And we wanted to take this instrument one step further. Can it differentiate between types of plastics? So we compared polystyrene on the right and PTFE on the left. And we can see that, unfortunately, the instrument can't differentiate between them because the peaks both lie at 600 nanometers. So both the spectrums fall within that tolerance. Although this instrument can't differentiate between the two plastics, what it can do is look for the spectrum, and it will highlight exactly where the plastic lies, which is shown by all the red dots. But so far, we've been testing clean conditions. We've just been ensuring that the instrument does what it says it does. We need to get closer to what happens in the environment. So we know in the environment, there's different size of nanoplastics, there's different surface groups or functional groups that could be on the nanoplastics, as well as various contaminants. So we proposed 3 research questions and went out and tested for them. We first tested different sized nanoplastics, 10 micron, 1 micron, and 0.1 micron. And we wanted to see, does the spectrum change as size changes? And we found that all the spectrums, again, fall within that tolerance. This answered our first research question, that size does not change the spectrum. Next, we looked at surface groups. we want to see if attachments or functionalized groups will change the spectrum. We tested our control group, which is the 10 micron polystyrene microbeads, with 20 micron polystyrene beads, which are functionalized. And we can see that again, when we compare the two spectrums, they fall within this tolerance. So this again tells us that surface groups does not change the spectrum. The last one is contaminants. This one's especially important because in the aquatic environment, you're not just going to get water. There's going to be different contaminants. So the first one we tested for is algae, which we think is a common contaminant that will be found in the water. And when we compared the two spectrums, we can see that the plastic mixed with algae and just the control group does not change the spectrum. It falls within the tolerance, which is good. So far we know what the spectrum of the plastic looks like. What about the spectrum for the algae? Well, we already confirmed that different elements have different spectrums, and we see that exactly for algae. What this allowed us to do, because the algae spectrum is different than plastic, we can ask the software to selectively only look for the spectrum of plastic, so that if we have a sample like this, we can identify exactly where the plastic is automatically. We repeated the same process with soil. We compared the spectrum, and we wanted to ensure that it falls within that tolerance. We knew what the spectrum for plastic looks like. We wanted to see what soil looks like, and we saw that soil has multiple peaks, and that allowed us to identify where the plastic is. So far, all three research questions were answered. But there's something else that we need to do to get a little closer to environmental conditions. That's the effect of time. Because remember, we said that the plastic bottle that we threw out gets exposed to the sun as well as temperature changes. So that happens over a period of 10, 15, or 20 years. So what we did is we try to mimic what happens over that long period of time in the environment in our lab in the span of 45 days. So we took different size nanoplastics and exposed it to UV light as well as temperature changes. And we're just taking out these plastics, and we want to see if the spectrum changes with the effect of time. Because if the spectrum doesn't change, what we'll be able to do is we'll one step closer to taking an environmental sample, say from the St. Lawrence River, bringing it to the lab and seeing if it has nanoplastics based on that one spectrum that we've identified. At the beginning of the presentation, I showed you this image of nanoplastics that could be in seafood. Now, those of you in the audience who are vegetarian or don't eat seafood were probably very relieved. But I'm here to tell you that it's also in the salt that we eat, that you use for seasoning. It's in the tea that you drink in the morning. It's also in rice, beer, and the tap water that we drink every day. After showing you this, you're probably going to ask me a few questions like, how much nanoplastic is in the environment? How much nanoplastic are we consuming? And at what concentration are these nanoplastics harmful to us? The scary thing is, I don't have the answers to these questions because we don't have an established method to detect these nanoplastics in the environment. But that's what the goal of my research is, to take these findings and pass it to the toxicologist or the marine biologist or a water safety technician officer so that they can answer these questions for you. My research is one step in this process of identifying what the impact of nanoplastics is on the environment and our health. Thank you.